Let's take a look at the sum and difference identities for cosine. So we have for two angles, alpha and beta, and they can be any two angles, that the cosine of alpha plus beta equals the cosine of alpha times the cosine of beta minus sine of alpha times the sine of beta. And the second identity I have is for cosine of the quantity alpha minus beta. I get cosine alpha times cosine beta plus sine of alpha sine beta. So what can we use these for? what are we doing? Well, I can use them, like in the next example, to determine the exact value of each expression. So in part A, I'm asked to find the cosine of 195 degrees. Now, I don't know what the cosine of 195 degrees is off the top of my head. 195 degrees is not an angle that we have looked at on the unit circle. But what if I'm able to break up 195 degrees into two angles that I do know something about? So in this case, I'm going to use 60 degrees and 135 degrees. Both of those are on my unit circle. So why don't I draw that over here? 60 degrees I can think of as, let's see, right there, and 135 is just 45 more than 90 degrees, so it's on that main diagonal right there. So this is 60 degrees, and the point here is 1/2 root 3 over 2. At 135 degrees, I am at negative root 2 over 2, comma root 2 over 2. Okay, so given that I have that, now I want to think, okay, well, what are we doing here? Well, cosine of 195 degrees is the cosine of 60 plus 135 degrees. Now this is only helpful because the formula ends up breaking this down into, let's see, cosine 60. Well, let's go back. First, I want to call 60 my alpha and 135 my beta. And I don't have to write that, but it's going to help me kind of think about um, what 60 and 135 degrees is going to replace when I am up here in this formula. Okay, so my goal is apply this top formula to what I have down here. So I have cosine of 195 degrees equals, write that as cosine of 60 plus 135 degrees. Now, why do I want that? Well, 60 degrees and 135 degrees, we just said, are these angles that we know where they're located on the unit circle. Now, if I had chosen, say, cosine of 5 degrees plus 190 degrees, that wouldn't help me, right? Because 5 and 190 aren't places I know on the unit circle, so that's not going to be helpful. But I did choose these nice angles. Okay, so how do I apply this formula up here? So I have alpha playing the part, or 60 playing the part of alpha, 135 playing the part of beta. So I can see on the right side of this formula, I have cosine, cosine, sine, sine. So I'm just going to write out kind of the structure of it. It's a cosine of an input, cosine of an input, minus sine of an input, sine of an input. Okay, so what am I going to put in there? Well, it goes alpha, beta, alpha, beta. So 60, 135, 60, 135. And I need to use my degree symbol. Okay, so now I'm going to have cosine of 60 degrees. So I'm going to replace that with its value, which is the x-coordinate at 60 degrees, which is 1/2. Cosine of 135 degrees, now I'm over here. That's the x-coordinate, negative root 2 over 2, minus sine of 60 degrees, root 3 over 2, sine of 135 degrees, root 2 over 2. Okay, I want to simplify, just multiplying everything out. I get negative root 2 over 4 minus root 6 over 4. And so I can write that as negative root 2 minus root 6 all over 4. That is the exact value of cosine of 195 degrees. All right, let's try it again down here. But now I'm dealing with the cosine of pi over 12. Now, I don't know any information about pi over 12 in terms of like my unit circle, say, but I might know information about two angles that could add or subtract to make pi over 12. So let's think about that. How would I know what would do that? Well, this is where I kind of just start playing around a little bit. And so you might need a little scratch work and you go, how am I going to make pi over 12 since that's my goal? Well, I might try something like, what's pi over 3? In terms of twelfths, that would be 4 pi over 12, okay? Then what about pi over 4, say? Well, pi over 4 is just 3 pi over 12, right? And now I can see if I do this subtraction, I would get pi over 12. So I start by writing cosine of pi over 12 as the cosine of 4 pi over 12 minus 3 pi over 12. This is a clear step, right? I'm just rewriting pi over 12 as this difference. But now what I'm going to do before I do anything else is rewrite each of these angles as what I would normally see them as. So in this case, pi over 3 minus pi over 4. And now I'm going to apply them into my formula. So pi over 3 will be playing the part, it's like a movie, of alpha, and pi over 4 will be playing the part of beta. And I'm going to use the formula where I have alpha minus beta since they're being subtracted here. So that gives me cosine, cosine, sine, sine. Okay, so cosine, cosine, sine, sine, and then I always forget if I have plus or minus there. Okay, that's a plus in the middle. And then how do my angles work? Alpha, beta, alpha, beta. Okay, so pi over 3, pi over 4, pi over 3, pi over 4. Remember not to use negative pi over 4 because the subtraction is already accounted for in the formula. Okay, looks like I might need a unit circle to kind of help me remember where these are. So if I draw my unit circle, I'm going to have one angle, pi over 4, and the other one is pi over 3. Okay, and so you can write out the points if you want to before you start, just to kind of make it easier. Let's see, for pi over 3, so this is pi over 4, and then pi over 3 a little bit farther, I get 1/2 root 3 over 2. Okay, so now I'm ready. These always take up a lot of room. There's a lot of terms. So cosine of pi over 3. That is the x-coordinate at pi over 3. 1/2 times cosine of pi over 4. Root 2 over 2. And then the plus sine of pi over 3. Now that's the y-coordinate at pi over 3. Root 3 over 2. What about sine of pi over 4? Y-coordinate at pi over 4. Root 2 over 2. Okay? And now I just get root 2 over 4 plus root 6 over 4. And if I want to, I'm running out of room to do it vertically, which I prefer, but if I run out of room, make a little arrow, and we can write this as root 2 plus root 6 all over 4. All right, lastly, let's look at cosine of pi over 2 minus theta. And I can think of this just like I've done before, where each of these are angles kind of playing a part. So if pi over 2 wants to kind of play the part of alpha and theta wants to play the part of beta, that just means in our formula, right? We can call those really just placeholders for whatever we want to plug in. So for the subtraction one, right, I just used it. I know I have cosine, cosine, plus sine, sine, okay? And I'm just gonna plug these things in. So what I'm really doing is I'm saying, okay, I have this expression. Maybe my cosine of the difference of two angles can help me simplify it. All right, so I know I go alpha, beta, alpha, beta. So I do pi over 2, theta, pi over 2, theta, right? Those that are playing those rules. Now I want to simplify. Well, cosine of pi over 2 is 0. So this whole thing is 0. But I can see that 0 times the cosine of theta, really cosine of anything, 0 times anything is just 0. Okay, let's keep going. Sine of pi over 2, this whole thing is just 1. Okay, so what do I get? Well, I get 0 plus 1 times the sine of theta, which is really just the sine of theta. Now what's neat here is I've kind of stumbled upon a cofunction identity. And a cofunction identity says that if you have two angles that add to be 90 degrees, so let's check the angles. Let's think of this as one angle right now. So the angle pi over 2 minus theta. Okay, I'm going to add that to my ending angle, which is just theta. These add up to pi over 2, which is really, we can also write as 90 degrees. So what I found is that this is really just my cofunction identity, which says that I have the cosine of this kind of starting angle is equal to the sine of this other angle. And these are cofunctions because this is true when the inputs add to 90 degrees or are complementary angles. And so I can see that these pi over 2 minus theta and theta are complementary angles because they add to be uh, 90 degrees from pi over 2. So we actually used this difference formula for cosine to prove the cofunction identity for sine and cosine.